one of the things that I told you earlier in the semester is there's no such thing as pure water. Now you can actually buy, I mean, you have to buy it from an industrial supplier, but they actually make ultra pure water.
I thought they're lying to us.
So Aquafina.
No, it's not. It's ultra pure because it has no dissolved solids or gases in it.
Oh.
Now, if you leave water out on the counter here, just put it in a cup out here, it'll absorb CO2 from the air. It'll absorb oxygen from the air, and that's not ultra pure anymore. Okay? But even in water that doesn't have any dissolved solids or gases, even in water with no dissolved solids and gases, all water molecules break up. Yeah, you could say divorce, sure.
No, they're probably not married yet.
Okay, now, it's a really, really small number of water molecules that do this at any one given time.
Right.
Okay? It's a really, really small number of water molecules that do this at any one given time. At any given time, at about, please, at any given time, at about 20 degrees centigrade, because it's temperature dependent, please stop.
My head is
Please stop. The concentration of hydrogen ions, or if we're using the Bronsted-Lowry system,
it's good.
okay, so this is using the Arrhenius system here, Bronsted-Lowry system here. Okay, because remember the hydrogen ions don't just go out there and just float around; they actually join up with waters. Okay. In any given instant in time, the concentration at 20 degrees C, the concentration of either hydrogen ions or hydronium ions, depending on which system you're going to use, is, let's see if I can do this right.
Looks good to me so far.
That's the concentration.
What temperature?
20 degrees C. Roughly room temperature. The hydrogen or hydronium ion. Now the way we symbolize that is hydrogen ion, we put it in a bracket. That means the molar concentration. When we put the symbol in brackets, it means the molar concentration. Okay? Pay attention now. Notice every time a water breaks up, if I get a hydrogen ion, I have to have a hydroxide ion, don't I? Can't. It's not possible to do it any other way. Okay, we're not creating and destroying matter here. Okay, we're not doing nuclear reactions. Okay, we have to have a hydrogen ion and hydroxide ion, or I have to have hydronium and hydroxide ion. So I'm going to do it according to Bronsted-Lowry. So if I have a concentration of hydronium or hydrogen that's this, if it's pure water with no acids or bases dissolved in it, and it's at around 20 degrees centigrade, then that is also going to be the concentration of the hydroxide ion. Okay? Well, let's see. It's easier to write that as 1.0 times 10 to the negative 7. Isn't it? Okay? So at around 20 degrees centigrade, pure water, no acids or bases, there are 1 times 10 to the negative 7 molar hydronium ions in that water. That's what I mean by there's no such thing as pure water, in the sense that it's all water molecules and nothing else. Okay? And then the concentration of the hydronium is 1.0 times 10 to the negative 7 as well. Okay? So this is the concentration of, the hydronium ion, and this is the concentration of the hydroxide ion.
Why is that one positive?
Hydronium is positive because it got a hydrogen ion. Okay? All right.
No, when you
talking about the exponent 7.
Oh, what?
It's not.
-7. I'm sorry, that should be -7. Really small number, right? If we multiply those two numbers together, this is the concentration of hydronium, this is the concentration of hydroxide. Multiply those together, we're going to get 1.0 times 10 to the -14. Okay, everybody got the calculator. That's a really big number, isn't it? A really, really small number, isn't it? Imagine putting a decimal place and 13 zeros before you put a 1 0 on the end. That'd be a lot of zeros, wouldn't it?
I don't want to write that.
Yeah, that's why scientific notation is helpful. Okay, it's not required here, but it sure is helpful. All right, got your calculator out?
Not yet. Hold up.
Okay.
Okay.
All right. Find your LOG button. Find your LOG button.
Whoa,
There it is. Got it.
Got it?
Okay.
What kind of log?
The LOG, not the LN. LN is natural logarithm. I want the log base 10.
log.
There are on scientific calculators two different log buttons.
Yeah.
There's the LOG, which is log base 10,
Yes.
and there's the LN, which is log based the natural number.
2.7.
Something. Okay.
Don't worry about it. No.
All right.
Hey guys.
So look, listen to me carefully now.
Okay.
Quiet.
Yes, sir.
I want you to put in LOG.
All right. Log.
Now, if it doesn't automatically give you a parentheses, put a parentheses there.
Mine automatically does
Okay? And then I want you to put in 1.0 E -7.
it.
Wait a minute. There's only numbers on
Mine
here.
gets a subscript too.
Huh?
Mine asks for a subscript.
I can't find my E.
Don't put one in.
Oh, never mind. I found it.
Where do you find the E button? Oh, okay, got it.
It's the double E.
The double E means times 10 to something.
Yeah, don't let it fool you.
Okay, what after we do that?
What do you get?
Enter?
I got -7.
I got -7.
You should get -7.
Yes! Tom, what'd you get?
Thomas got it wrong.
You wrong. You're wrong.
Hey.
All right. Now listen. Listen. Somewhere on your keyboard, you've got to change the sign button.
You're right.
On some keyboards, it looks like this. On other keyboards, it looks like this. But I won't change the sign of that. What do you get? Of your -7. Exactly. All right. In pure water, what do you expect the pH to be?
-7.
7. Okay. Well, we just calculated the pH of pure water, and what pH is the negative logarithm of the molar concentration of the hydrogen or hydronium ion concentration.
So it's actually 7, but it's actually negative. Or is it -7?
The pH is 7. When you change the sign of this, you get a positive 7. So if I put a negative logarithm in front of it, I'll get a positive 7.
So you can do -1.
That's right. You put in your change of sign. Well, it depends on your calculator. Some calculators you can put it in as negative log this number and get the right answer. Sometimes on some calculators you got to back into the calculation. You put in usually I think you put in 10 to the -7, then hit the log button, then hit the change of sign button. Then you have to know how your calculator works. And that's what's kind of complex sometimes. Okay? You have to know how your calculator works to calculate pH.
You have to be smarter than your calculator.
That's right. You have to be smarter than your calculator. Yes?
So why did we plug in 1.0 E -7 if... Oh, never mind, I was kidding.
All right. All right.
Like.
So,
Either way, we're either counting the hydronium or the hydroxide depending on what we're doing. after.
exactly. Exactly. Now, pay attention. So the pH
Right.
then of this pure water then
7.
7. There is also a pOH.
7.
7.
Bam!
Yes.
So they're always the same thing?
No.
Is when it's pH and pOH, is it always going to be with the exponent times 10?
If your the number here is 1, yes. But if the number is something other than 1, it gets a little, that's why you need a calculator. Now, when I was in high school, we didn't have calculators. Actually, we had when I was in school, the electronic calculators first came out. And my calculus teacher would not let us just use calculators like you're using in here. We had to use something called a slide rule.
Oh! Show us how to do it.
I remember when I used
I don't
it
even
back
remember.
when I was a
Did you
Egyptian.
carve numbers in stone?
I remember I wrote hieroglyphics.
Yeah, I was living back in the day.
You can't spell hieroglyphics.
Yes,
All right.
Spell.
All right, please listen.
It's good.
I got a couple more things to tell you before you can go home today. You want to wait on your questions a second?
No way.
Or not?
I was just gonna ask, do we always put a negative on?
I can't hear you. Do not put your notes away. I'm not done. Go ahead.
Do we always put a negative for the
If your calculator will let you do that, that would be the way to calculate the pH or pOH from the concentration. All right. Listen. You got to be still and listen.
What?
I said be still and listen.
I know, I just put my hoodie on.
2 parts.
No,
Okay.
You're right.
14.
Yeah.
That's the maximum range of the pH scale because of this. Okay? Now this number right here, when I multiply these together,
Bless you.
is a very important number. Alright? Anytime now if I change the hydrogen ion or hydronium ion concentration, this concentration changes, so this number is always constant.
Thank you.
You listening to me?
Burn.
If I change this number by adding an acid to the water, this number changes, so this answer is always this. And this number right here then has a special name, and it's called the autoionization constant. Actually, let's make it KW. K, autoionization constant for water. You need to know by memory this value, and this value. And this value is always, regardless of what these are, this is always the autoionization constant of water. 1.0 times 10 to the negative 14 molar is the actually it's molar squared, is the autoionization constant. Is the autoionization constant for water. And it's the basis for the fact that the pH scale has a maximum of 14. Does that make sense?
Yes, sir.
Remember, you're supposed to annotate and get ready for the lab on Monday.
Got it.
All right, have a good weekend.
You too.
You too, Mr. Taylor.
Go home. Have a good Thanksgiving.
You too.
Go Randolph.
All right,
Oh, God,
Thanksgiving.
Tom.
All right.